Take a heavy atomic nucleus, like uranium, and look at it through the lens of basic electromagnetism. You'll realize it shouldn't be able to exist. You have dozens of positively charged protons packed into a space measured in femtometers, a scale so unimaginably tight that it generates immense electrostatic Coulomb repulsion. According to the laws of physics, this arrangement should detonate instantly. The outward push of that many positive charges in close proximity is overwhelming. The only reason these structures don't tear apart is the strong nuclear force, a short-range, intensely powerful pull that overpowers the electric repulsion. This microscopic tug-of-war sets the parameters for all complex matter and dictates the release of star-level energy. To understand the behavior of the entire periodic table, we first have to strip away the whole nucleus and look closely at the interaction between just two single nucleons. Looking at this rule in our source notes, we see that the nuclear force operates with strict universal parameters that are completely independent of electric charge. Whether it's a proton-proton pair, a neutron-neutron pair, or a proton-neutron pair, the strong force mechanism locking them together is exactly the same. Mapping the parameters of this microscopic rulebook allows us to accurately predict massive macroscopic phenomena, including both nuclear fusion and nuclear fission. The energy released in a nuclear reaction follows a predictable geometric pattern governed by the single physical force. This graph shows the potential energy between a pair of nucleons as a function of their separation distance. Starting on the right, beyond roughly 1.5 femtometers apart, the strong force is effectively zero. They don't interact at all. But as they cross that 1.5 threshold and move closer, a violently strong attractive force takes over, dropping their potential energy dramatically. The curve reaches its absolute minimum point at about 0.8 femtometers, the precise distance of optimal attraction. If they are forced closer than that 0.8 mark, the dynamics instantly flip. The strong force becomes intensely repulsive, shooting the potential energy nearly straight up. This severe repulsive core provides a physical barrier. It is the exact mechanism that prevents an atomic nucleus from collapsing in on itself into a singularity. This narrow pocket of space, trapped strictly between pulling inward and pushing outward, dictates the constant uniform density of all nuclear matter in the universe. Now take those two nucleons and scale the system up. Picture a single nucleon buried right in the center of a massive atomic nucleus. Because of that strict 1.5 femtometer drop-off we just saw on the graph, our central nucleon can only bind with the nearest neighbors, physically touching it. We call this state force saturation. Once a nucleon is fully surrounded by its immediate neighbors, adding more nucleons to the outer edges of the atom does nothing to increase the central nucleon's strong force bonds. This is entirely different from gravity or electromagnetism, which extend infinitely outward and compound in strength as you add more mass or more charge to the system. By maxing out at its nearest neighbors, force saturation places a strict mathematical ceiling on how tightly any atomic nucleus can be bound together. This chart plots the binding energy per nucleon against the total mass number. It is our ultimate metric for evaluating how stable an atomic structure is. Look at the rapid rise on the far left. In very light, small nuclei, saturation hasn't been reached yet. Adding a new nucleon significantly increases the overall stability of the cluster. But as atoms get heavier, the curve levels off into this wide, flat top. This plateau is the direct macroscopic proof of force saturation. The binding energy maxes out because every internal nucleon is fully surrounded. The absolute peak of this plateau sits at iron 56, hitting a maximum binding energy of 8.75 mega-electron-volts per nucleon. Sitting at the top of this curve means iron 56 rests in the deepest thermodynamic well in the universe. It is the ultimate state of physical equilibrium that all matter attempts to reach. A basic rule of thermodynamics states that physical systems will spontaneously reconfigure themselves to reach a higher state of binding energy, which naturally creates a lower total energy state. These notes outline nuclear fusion. When lightweight, loosely bound nuclei combine together, their mass increases, moving them up the steep left slope toward iron and tightening their bonds. Transitioning to a tighter binding energy state means the system requires less total energy. It expels the difference, releasing the immense energy that powers stars. On the far right side of the curve, extremely heavy elements face the opposite problem. Their massive size actually lowers their binding energy per nucleon, making them less stable. Checking the handwritten notes at the bottom of our chart, we see how this leads to nuclear fission. A heavy nucleus gains stability and climbs back up toward iron by splitting into lighter, more tightly bound nuclei, again releasing massive amounts of energy. Fusion and fission function through the exact same thermodynamic mechanism, matter reconfiguring its geometry to climb the curve toward the ultimate stability of iron 56. To understand why the heaviest atoms become unstable in the first place, we have to look back at the problem of Coulomb repulsion, because unlike the strong force, electrostatic repulsion does not saturate. As you build a heavy nucleus, every new proton you add pushes against every single other proton across the entire atom, constantly compounding the outward pressure threatening to shatter it. This graph showing the ratio of neutrons to protons reveals nature's exact mechanism for combating compounding repulsion. Light nuclei achieve stability at a 1-to-1 ratio, but as we move to heavier elements, surviving atoms diverge completely from that even line. Heavy nuclei require a heavy surplus of neutrons to survive. Neutrons supply additional strong force glue to hold the atom together, but they do it without adding any extra electrostatic repulsion. If a nucleus is built outside this strict band of stability, it will undergo beta decay, literally converting its own protons into neutrons or neutrons into protons to force its internal ratio back to the correct mathematical balance. Beta decay is an active structural correction, preserving the balance between the strong force pulling the atom inward and the electrostatic force pushing it outward. The vast complexity of nuclear physics and the behavior of dozens of interacting particles across the periodic table are dictated by a rigid geometric balance. The 0.8 femtometer minimum in the potential energy well defines exactly how closely matter can physically pack itself together. The 1.5 femtometer drop-off creates force saturation, generating the binding energy plateau that restricts how large a stable element can grow. And the compounding repulsion of the protons dictates the exact neutron ratio required to keep the heaviest atoms intact. The exact microscopic shape of the strong force's potential well dictates the macroscopic behavior and the ultimate thermodynamic fate of every atom in the universe.